Welcome back to this plenary session. I hope you enjoyed this afternoon's sessions and talks. I'm really delighted to introduce our second plenary speaker, Professor Peter Robinson. He was very kind to give his time to us again this year, having already reserved the time for last year before everything was postponed. Professor Robinson is a professor of computer technology in the computer laboratory at the University of Cambridge, where he leads work on computer graphics and interaction. His research concerns the problems at the boundary between people and computers, and this involves investigating new technologies to enhance communication between computers and their users, and new applications to exploit those technologies. The main focus for this is human-computer interaction, where he's been leading work for some years on the use of video and paper as part of the user interface. He's also led investigations of the inference of people's mental states from facial expressions, vocal nuances, body posture and gesture, and other physiological signals. His talk today will be on the computation of emotions, and I'm delighted to hand over to Peter now. So Peter, thank you very much.
Well, thank you very much. Thank you for the welcome. Thank you all for your time. And I'm sorry, it's the end of a long day, so I'll try not to rabbit on too long, but we'll see how it goes. So you don't often hear computer scientists talking about emotions. You know the characterization of the extrovert computer scientist is the one who looks at your feet rather than his own when he's talking to you. But I'm interested in emotions, and in a broad sense. I'm interested in communication between people and machines, and we can inform a lot of that by an understanding of the way that people communicate with each other. And we communicate in lots of ways, not just the words that we're speaking or what we're writing down, but through things like facial expressions. And understanding those is an important part of human communication. When actually one of the difficulties of speaking to a remote audience like this is I can't see your faces. But if we're in person, I could see your faces, and I could see if you were interested or bored, confused or understanding. And I would build a mental model of that. It's the thing the psychologists call mind reading. And if you were at Andres Peas's talk on mind reading and trust in robots, you'll have heard a bit about this earlier this afternoon. And people who can't do it are at a social disadvantage. It's people with autism spectrum conditions. And in that sense, computers are autistic. They ignore these signals. So we've been wondering whether we could do something about it. And to start about this, we had to think about human behavior, and this goes back a long way to a great Cambridge scientist, Charles Darwin. Shortly after Darwin published his work on the origin of species, he also became interested in the expression of the emotions in man and animals. He wondered if there was a universal language of emotions that people and perhaps animals, other species, expressed through their faces. And that would give them some sort of evolutionary advantage. They would see these and they would see signals of aggression or affection or whatever it might be in the other species. And in fact, Darwin published his book on this in 1872, and rather unusually for a scientific textbook, it was a bestseller. It completely sold out in 2 weeks. And it was a very interesting book in that Darwin was one of the earliest scientists to use photographs in his work. And he collaborated with Guillaume Duchesne de Boulogne in Paris, who had been taking photographs of people showing various emotional expressions. And Darwin had a set of Duchenne's photographs and used these to study emotions in people. In fact, the illustration on the screen now shows you a page from Darwin's book, and you can see a set of the Duchenne photographs in the column on the right. Duchenne worked a lot with a particular tramp that he pulled off the streets of Paris. And you see a neutral expression at the top him with a natural smile, insofar as he could smile naturally, not having any teeth, in the middle, having been told a joke. And in the bottom picture, Duchenne had attached electrodes to the muscles in his face to force a smile to see if that amused him. It didn't, but experiment that had to be done. And the photographs on the left are from Darwin's own collection. A genuine smile at the top and two posed smiles at the bottom. And one of the questions that interested Duchenne in particular was, could you distinguish a genuine smile from a pretend smile? As I say, Darwin was interested in knowing whether these expressions were universal, and he set about doing this by crowdsourcing. He took his photographs, the big plate photographs that Duchenne had sent him, and showed them to people. Now, crowdsourcing in the 19th century was a bit different. What Darwin did was invite people round to his country house, and over drinks before dinner, he passed the photographs round and asked them what they perceived and put the answers in a spreadsheet. Now, we actually have Darwin's collection of Duchenne photographs in the library here in Cambridge, and also the spreadsheets. They were, of course, paper spreadsheets. And we reproduced Darwin's experiment a few years ago by digitizing the Duchenne photographs and putting them on a website. And we had about 20,000 people crowdsourced annotations online. And here you see the photographs that we used, 10 of the photographs from the collection, and also some pictures of Darwin's original spreadsheets. It's got the names of the guests across the top, and the names of the photographs down the side, and the expression that they saw written into the cells of the spreadsheet. And Darwin saw that there was a consensus view. And in fact, the labels under the photographs, the top line are the consensus labels that Darwin saw, and the lower labels are the consensus labels that we got in our more recent online crowdsourcing. And you can see that they're actually pretty similar, albeit the wording's a bit different with the passage of 130 years, 140 years. So it would seem that there is a universal expression of emotions in the face. Now, actually, that view fell into disrepute early in the 20th century, partly as there was a bit of a backlash against Darwin. And it was really revived by the American psychologist Paul Ekman, who thought maybe there was more to this and set about testing Darwin's hypothesis a little bit more scientifically than perhaps Darwin had done. So Ekman looked at the emotions that Darwin had described in his book. There were actually 7 in Darwin's book, and identified these as being 6 more distinct categories. And here you see the prototypical facial expressions that Ekman used in his work: anger, disgust, fear, joy, sadness, and surprise. And Ekman also took these photographs and distributed around the world. Now, in Darwin's day, the photographs were extremely expensive. Darwin only had one set. He couldn't send them around the world to see if different cultures actually saw the same emotions in the faces. In fact, what Darwin did was send a questionnaire around the world, because he could post that and it would get the results back a few months later. But I have to say that by modern scientific standards, it wouldn't really pass muster. The questions were essentially leading questions. Do you perceive happiness when the mouth turns up at the edges? That sort of question. It wasn't perhaps the best way of running a study. Ekman, on the other hand, could use these photographs, post them around the world, and ask what emotions people saw. And it turned out there was still a pretty universal understanding of these 6 basic emotions. They're fairly visceral emotions. You can see that they're ones that might be relevant for survival. You need to know if another person you're talking to is getting angry. you might need to know if they're disgusted. It might mean they've eaten something that's bad for them. And in fact, these are things that we do recognize very easily. Those of you who enjoy cartoon movies may have seen Pixar's film Inside Out, which depicts the workings of a young girl's mind as competing emotions. And in fact, the emotions that you see here are anger, disgust, joy, fear, and sadness, 5 of those 6 basic emotions. You don't get surprise in Disney films, I suppose. But it just means that these are well known in the acting profession. And actually, that's been known for a long time as well. If we go back to quite early in the 20th century, when moving films were just beginning to take off, it was rather important that an actor could portray emotion in their face. And the pictures here of a Hollywood starlet called Florence Lawrence, who was known as the Biograph Girl. And in 1909, she was making 3 feature films a week. 3 films a week, a level of productivity you don't see in Hollywood nowadays. Now, there were reasons for that. One was the films were only 20 minutes long, because that was as long as you could fit on a reel of film. And they were silent, so she didn't have to learn her words. But she did have to express emotions. And this was her advertising card, and it shows the range of expressions that she could portray just through her face. And we know that she was an actress, she was expressing emotions, but we know that facial communication is an important part to enhancing communication. It's where you show empathy, you nod in agreement, you acknowledge people. And in fact, facial expressions don't just convey these basic emotions that Darwin and Ekman studied. There are also complex mental states, thinking, understanding, that aren't quite so obviously inferred. In fact, in this picture of Florence Lawrence, the picture at the top left is labeled piety, and the picture bottom right is labeled sadness. And I reckon they're indistinguishable, piety and sadness. Now, that may say something about the morals of Hollywood starlets, even early in the 20th century, or the fact is these are complex emotions and you can't actually recognize them from a still picture. Well, the more modern study of emotions, we're very lucky in Cambridge. We have a research centre that works on autism, led by Simon Baron-Cohen, Professor Sir Simon Baron-Cohen, who is interested in the pathology of autism and possible interventions to help people with high-functioning autism recognize emotions. And as part of his work, some years ago, he prepared an analysis to try and identify rather more words describing mental states in people. And what he did was to take the dictionary that's used for the spell checker in Microsoft Word, it's got about 1,200 words in it, and then worked out which ones were synonyms for each other and worked it down to about 400 very finely nuanced different emotions and gathered those into 24 broader categories. And these broader categories are interesting. 6 of them are the basic emotions that we've just seen from Darwin and Ekman. So fear, anger, disgust, happiness, sadness, surprise. And those are the ones that we can recognize easily and probably recognize from still photographs as well. And then the other 18 of these broad categories are the cognitive mental states, the ones that show what you're thinking. So things like bored, which matters when you're giving lectures, or confusion, which perhaps matters, romantic ones, and so on. And these perhaps are more important for predicting intentions and actions. We don't actually experience the basic emotions very often. We may get annoyed with our computer when it doesn't function properly, but it's not the same as the sort of visceral anger that you get when somebody's hit you with a rock or something. Well, given that classification, what Simon Baron-Cohen did was then to get actors to record each of these 400 or so finely nuanced mental states, and prepared a DVD with 6 examples of each of the 400 or so on it. And these were acted, and then he had a panel of 10 psychologists who looked at the acted version and said whether or not it was an acceptable representation of the emotion, and only if 8 of the 10 agreed was it included. So quite a lot of the acting went on the cutting room floor. And Simon's hope was that this DVD could be used as a training tool for children with high functioning autism, Asperger's syndrome, that they could look at these videos and learn the characteristics of what was happening. That these are children who know that they can't recognize emotion, want to, and are intelligent enough to learn about it. Well, what it turned out was that the children got very good at recognizing any of the 2,500 videos on the DVD, but they couldn't generalize from it. They couldn't work from those DVDs to other bits of video, perhaps some of the spare acted video, or even everyday situations. And well, that's an interesting question. We'll come back to that later. It turns out that what they need is a bit of context, and Simon has done subsequent work with videos worked into stories. So rather than just acted video, stories wrapped around them. And with the aid of those stories, the children can actually learn to recognize emotions and understand people's emotions, which is terrific. However, this DVD may not have been a great training tool for children, but it's a brilliant training tool for machine learning systems. And so one of the first things we did was wonder, well, how long do you have to watch video? We could see that it mattered that you had a movie, not just a still picture, but how long does it have to be? So we took some of the video clips off the DVD and cut them up into shorter segments, and then showed people initially just the very last fifth of the movie, and then the last 2/5 and 3/5, 4/5, and then intermingled all these and worked through the 24 clips. So we had 16 showing complex mental states, 8 showing basic emotions, and they were all various different lengths, but then cut up into 5. And we got lots of, well, 3 dozen participants to look at them and ask them what they saw using a forced choice. And the graph at the lower right shows you what happens with the basic emotions. The recognition rate on a forced 4-way choice is about 3 and 4, pretty well consistently, no matter how long you show the video. In other words, you can recognize basic emotions from still pictures. But with the complex mental states, we found that the recognition rate rose from about 50% up to 70% as the length of the video clip went up to about 2 seconds, and then it leveled off. After 2 seconds, you couldn't really improve much more. So that told us that we would need to analyze moving video if we wanted to understand complex mental states. And so I had this is, of course, as is the way of academia, a very bright research student who put together a system that actually did this. So tracking feature points on the face, you can then, feature points around the mouth, the eyes, you can actually work out the head pose, so whether it's up, down, left, right, or whatever, and then also the various facial features. And then from those, you can infer action units. Action units are a language that psychologists have used, well, actually since about Ekman's time, for a scheme that he devised for describing facial expressions and head movements in video. And normally these are manually annotated, but we could derive them automatically. So, for example, from the pose information, we could tell whether your head was up or your head was down, your mouth was shut or open, and indeed, when it's open, by doing a bit of color analysis, whether it's open, as it were, in surprise, or open with laughter, which tends to show the teeth more. So we could identify these different action units, and then from those we could infer gestures, if you like, displays. So nodding is a sequence of head up, head down actions. And then finally, we could infer from the gestures the mental state using a bit of history, so building up over about 2 seconds. And the resulting system operates a bit like this. Here you see somebody who's being asked to act as if she's agreeing. And the little bars on the side are showing the action units and the gesture, or the gestures, in fact, that she's giving. And the graph across the bottom shows the inferred mental state. And here you see an inferred mental state. The red is agreeing, and you see that after a couple of seconds, the system kicks in. It recognizes some agreement. If I replay it, you'll see this actually happening. So there's a bit of agreeing, and then she paused for a moment, and the strength dips, a bit more agreeing, and then there's a little bit of burst of green. She's interested to know if it's worked. She's asked to do a bit more, so a bit of blue, which is concentration, and then a bit more agreeing, and then it's over. So this was, I mean, of course, I picked this video because it happens to work well, but it gives you an idea of what this system did. And we then did more serious experiments using half a dozen conditions which we thought would be interesting for interaction with computers. So things like agreeing, concentrating, disagreeing, interested, thinking, which is perhaps the same as concentration, and unsure. That's uncertainty in the person, not uncertainty. And this is this video clip is one of the Baron Cohen videos, and you could speculate as to what you think the emotion is. If I had a real audience, I would take an extremely unscientific poll, and I'd discover that, well, actually, you never get a unique answer. It's not as if everyone agrees. Some people will see more than one emotion there. But typically, this is what we actually get out of our system, and actually it reflects pretty well what we see in the audience. Some people see that early pink trace, which is disagreement. And if you just look at the very beginning, you might think she was disagreeing. The brown and yellow traces are, brown is concentrating and yellow is thinking. And I said it's perhaps a fine division between the two. And in fact, this video was, the finely nuanced state is called brooding, and it's part of the thinking group. And yellow is our inference of thinking. And if you wanted to label the whole video automatically, well, yellow has the biggest area under the curve, so you'd probably call it yellow. So it's actually working. But it does show you that this is in no sense a binary choice. We are not going to get explicit answers out of this system. It's hints, it's soft information. But we know that's the way that artificial intelligence works. You have to take it on a statistical basis. Well, what my student did then was take some videos and doing extensive training and leave one out analysis, worked out the recognition rate. And here you see a confusion matrix with the 6 different conditions that we were looking at, which together cover about 10% of the whole range of emotions on the disk. So it's only a small section, finely divided into 6. And across the horizontal axis, you see the ground truth, and going into the depth, the inferences from the system. And you see various things here. One thing you see is a pretty strong diagonal, which is encouraging. And you'll perhaps see that the tallest one is the green bar, which is concentration, which is almost 90%, being recognized 90% of the time. And the least accurate one is thinking, which is only being recognized about 65% of the time. But if you look at the confusions for thinking, you'll see green, which is concentration, yellow, which is interest, and black for uncertainty. So those are actually fairly reasonable confusions. And it's just a lesson about this sort of inference system, is you can't rely on it to give you a labeled truth. Although it turns out that some people do think that, and another way of looking at emotions sort of leads us into this. And a Canadian psychologist, Jim Russell, was interested in trying to find other ways of representing emotions. Simon Baron-Cohen's system, building on Ekman and Darwin, used a large taxonomy of words. Jim Russell tried to see if there was a way you could describe them by numbers. And he did this by getting people to take little labels with emotion words on and spread them out on a table so that similar emotions were together and different ones were far apart. It's a sort of principal component analysis, actually. And what you see here is that they divide up. There's a horizontal axis here, which is known in psychology as valence, going from negative emotions on the left across to positive emotions on the right. So from gloomy and depressed on the left over to happy and satisfied on the, sorry, where's that? Right, over to happy on the left. And there's a vertical axis that's appeared, which is activation, from passive at the bottom, sleepy, bored, up to active at the top, alarmed, excited. And of course, you can be negative and active, that's something like alarmed, and you can be positive and active, that's something like excited, and so on. So this sort of spreads the emotions out around a two-dimensional plane. Of course, that's just because he had a table that they were laying the words out on. There are also other dimensions. These two dimensions cover about 50% of the variability in the coordinates of the data. And there are other axes with much less influence. So potency, is it a weak or strong emotion? A tendency, is it an inward or outward expressed emotion? But this dimensional description has appealed a lot to many computer scientists because they think, oh, good, I've got some coordinates for this emotion. And indeed, it's true. You can label the videos using coordinates and then train a system to recognize them. So this is a later version of our recognition system, slightly different face tracker now. You can see the histograms across the bottom are showing the various action units, so brows raising, a smile forming, and so on. You can see the categorical labels appearing on the right, and also a trace wandering around the two-dimensional valence activation space at the top. And what we discovered, and of course obvious to anybody who knows anything about this sort of machine learning, is it depends hugely on the training data. And of course there are no absolute values for the dimensional description of an emotion. So somehow you've got to try and rely on these numbers that people have attached to different emotions, and it turns out they're really not very good. And we can see that if we take a load of videos, in fact, one's again from some of the training data from a later project with the Autism Research Center, and we can actually look at the prediction intervals in the two-dimensional space. So here you see a large ellipse, sort of in the vaguely positive, vaguely active area, which is surprise, and a longer, thinner ellipse. So these are the sort of 95% confidence intervals round lots of samples. So you get lots of individual points, put a 95% prediction interval around it. And you see it in 2 dimensions here. And happiness, rather more positive, actually rather more active, but of the 6 Ekman emotions, the 4 negative ones, fear, anger, disgust, and sadness, overlap significantly. So this sort of dimensional analysis is never really going to distinguish those accurately. And that's a major problem about this. But there are still things you can do here. So the important thing is when this work was in its early days, 15 years ago perhaps, people had great hopes for being able to read people's minds, that is, understand their mental states, and have computers that reacted, because you just pull out the coordinates for their face and that would tell you what they were thinking. Well, this diagram shows that that's a nonsense. There's too much overlap. But what you can do is get quite a good separation in the valence space. And so you can actually see perhaps how happy, satisfied somebody is. And there's maybe even a scale with some quantitative meaning running horizontally. And in fact, the student who did a lot of the early work now runs a quite successful company in Boston called Affectiva, where she's using these techniques to measure, well, her first big market was measuring valence of audiences watching draft versions of television commercials. So you show the commercial to an audience, and normally what happens is the individual people watching it are monitored and somebody writes down the action units that they see them displaying. With this system, you could just point a camera at a room full of people, analyze their faces, and make an inference, make sure that they were amused, happy, pleased at the right points in the commercial. A more important application of this that they're developing now is monitoring people in cars. As cars get more and more automation in them, there is a concern that the driver will not really have to do much in order to drive the car, and might stop concentrating, might fall asleep. You can detect that quite easily, actually, but might just be distracted. And so it's quite important that the car monitors the driver to make sure that they're able to take over when the automated system in the car isn't capable of continuing. And so Affectiva have collected enormous amounts of data of real car drivers. They got lots of people driving around Boston and other cities in the world to put cameras in their car, recorded it. They then got it all quite carefully labeled. And then now they have millions of samples of, tens of millions of samples of facial expressions that they can use to train their machine learning systems. And meanwhile, we've done something similar using this as part of a big European project to try and make, again, a training tool for children with high-functioning autism spectrum conditions, where they played various games to try and learn about emotions. And then we wanted, one way to learn about them is to act them. And so we wanted children to act out emotions and then give them feedback about how well they were acting. So in fact, we monitored their facial expressions, this thing that we've done a lot of work on in Cambridge, some work on voice from some colleagues in Munich, and some work on body posture and gesture, which is actually another channel of expression from some colleagues in Genoa. And we could then feed back to the children how well they were acting the emotions, and that would help them learn how to recognize them. And this is actually part of the system here. You see one of the video clips, top left, somebody trying to imitate it, top right, and then the action units being inferred. And the little chart at bottom left is showing things that need to be emphasized more or emphasized less in order to track the video exactly. And that actually turns out to be quite a useful way of training children to recognize emotions. Well, actually, this led us on to another thought, partly because our department happens to be opposite the veterinary school in Cambridge, and they happened to come to one of our open days and saw some of this work. And they said, that's really interesting. We've been studying sheep, and sheep have quite expressive faces. Could you analyze the faces of our sheep? And we thought about that. And going back to Darwin's book was on the expression of the emotions in man and animals. And Darwin actually gave some time to expression of emotions by dogs, cats, horses, actually, he was interested in. So there was some pictures from Darwin's book at the top left there, a dog and a cat prepared to fight, and you can sort of see hackles raised, arched back. And then bottom right, as Darwin put it, in an affectionate frame of mind. And again, you sort of recognize that there's a lot of body posture in this. Well, we were interested in sheep faces, and it turns out that the vets in Cambridge had developed a scale for quantifying the expression of pain, in particular, in a sheep's face. They don't laugh much, but they do show pain. And sheep are actually quite often in pain. They get foot rot in their feet if they've been out in the field too long. It's quite important to recognize this. They might have mastitis, other things like that. And the sort of things that happen are their eyes close. So the top row is healthy animals, and they're sort of getting more and more pain as you work down. So you can see the eyes close into slits, the cheeks sort of draw in, the ears actually rotate, sort of fold down as they get into pain. The lower lip draws back, and the nostrils move from a sort of shallow U shape in a happy sheep into a rather sharper V shape in a sad sheep. Now, I actually rather like walking in the hills, so I now spend a lot of my time as I'm wandering around the Lake District fells looking at the sheep. And I can, actually, it turns out it's really rather fun recognizing what a sheep might be feeling. Anyway, we thought, fair enough, we can apply our facial analysis to this. We just got to track the face of the sheep, pick up some feature points, and look for things like movements around the eyes, the ears, the nostrils. And here you see some pictures of a flock of sheep. And these are, the whole flock of sheep has been photographed at once, exercise for the reader. How do you get a flock of sheep to look at the camera when you take a group photograph? You can ponder about that. The system is then identifying where the sheep faces are, which is sort of possible mostly, although you'll notice one or two sheep who actually aren't facing the camera, like they got their back towards the camera. So that's not so easy for analysis. And you'll see that they've got boxes round showing that we've identified faces. And mostly they're green boxes, meaning they're happy sheep. You can actually see rounded nostrils, open eyes, ears upright. And one or I think two of them actually have red boxes round showing moderate pain. And the example that's at the bottom, you can just begin to see the ears are beginning to fold down. The left ear has folded down slightly, the right ear hasn't. The nose has begun to change shape, and those are indications that it's possibly in pain. And there's actually a continuous, well, a 3-point scale for each of the indicators. So you get a 15-point scale for a whole sheep, and we can pitch the sheep on this. And it turned out those two sheep were indeed the ones that had problems in this flock. I have to say, the research student who did this rather bravely volunteered to go on the BBC programme Countryfile. So these sheep are actually, one of the presenters keeps a flock of sheep, and she actually pointed webcam at them, took this picture, and he agreed they were the sheep that were in pain. So that was extremely pleasing. If I a bit nervous about that, but at least it was recorded television. So if it hadn't worked, they'd just have dropped the item. Well, I mentioned in the context of training children with autism that another thing that matters is things like speech. And one of the things that's interested us is non-verbal aspects of speech. Now, that's much more difficult because you don't actually have the characteristics that you can describe in a face to do with ears and eyes and so on. And in fact, it's quite hard to, speech is very complex. It's multidimensional in all sorts of ways. You've got tone, pitch, energy, and to analyze these, you sort of look at frequency bands and energy in the different frequency bands and derivatives of these and so on. And it turns out that you can do some sort of principal component analysis, which allows you to separate two classes of mental state. But beyond that, it gets a bit difficult. So you can do pairwise comparisons quite accurately. And then what you do is use some sort of voting system to combine the pairwise votes, a sort of preference voting, if you like, and you can then get a preferred mental state. But if you use the right voting system, you can have a multiple seat constituency, as it were, in the voting. So you can actually have several winners. And that's not a bad idea because people do express more than one mental state at a time. And the result for this, these are the same sort of confusion diagrams. There are 9 different conditions here. The top left picture shows you with a single winner, again, fairly strong diagonal, and the bottom right shows you the possibility of multiple winners. And actually, this turns out to be a more useful tool. And we even managed to use that to do some analysis of public speaking. So you can measure the voice profile of a person and sort of see how fluent they are. Are they changing the loudness much? Are they just too loud or too soft, and so on? And you can draw a little diagram. This was with a local company that trains public speakers, and we found we could actually build a tool that helped them with their analysis. Likewise, I mentioned another way you express emotions is through gestures. So if you have these facial expressions of tennis players, you can see there's a fairly strong emotion in play there, but not necessarily identify what it is. But if you show a bit more of the body, you can see some are despair, typically an open hand downwards, and some are victory, which is a clenched fist raised. So body posture and gesture is important, but monitoring it's more difficult. We were doing this work some time ago before you could buy domestic systems. So you actually had to put a rather fancy reflective leotard on and then use a multiple scanning system to monitor what you're doing. And you can sort of see a sad or an angry acting there. Well, of course, this is also usable for measuring emotions, and we've got some videos actually from some colleagues in Glasgow who recorded 4 different activities with 4 emotions and had a large number of subjects recorded and tracked them using similar equipment. And it turns out this is really much more difficult to analyze. I mean, firstly, you have to wear a fancy suit. Well, not nowadays. You get a Microsoft Kinect and you can do it. But what you discover as you analyze it is what the person is doing. So you have to factor that out. And that's a matter of breaking the motion up into separate components. So a knocking action, there's a sort of a lift and then a strike, retract, strike, retract, strike, retract, and then drop. And as long as you can separate those, and there's a sort of gap in the movement, if you like, a low energy point where you can break it up. And then you analyze each of those in turn. And what you then find out, you discover, is who's doing it. So this actually, unlike facial expressions and voice, which generalize well from training data to on one person to other people, these tend to be rather personal measures. And when we measured them, we had to do, first of all, the segmentation, which actually gives a small improvement, but then training it on an individual to remove bias turns out to be quite important. Well, there are other ways you can measure emotion. A lot of people use physiological measurements. We've avoided these because they're a bit invasive. So skin conductivity is actually a very good way of measuring arousal. It turns out you sweat a bit when you're, and that decreases the resistance of the skin, and you can measure that. Your heart rate changes, or in particular, the variability of that is a strong indicator of arousal. Some people think you can strap electrodes to the head and spot what's going on in the brain. I mean, to some extent that's true, but probably not with a cheap domestic kit like this. Or indeed just put someone in an MRI machine and see where the activity in the brain is. And that's also maybe useful, but it is a fairly invasive procedure. But we've done work with this, wearing essentially things like a glorified Fitbit to do long-term monitoring of people. And actually the most useful thing you can measure is their activity level. And we've seen with patients who've got long-term treatment for depression, you can see that their activity levels on a day are often correlated with, as it goes down, there's likely to be a depressive incident coming. And actually that means you can make an intervention before they do something serious. Well, the other thing that we were vaguely interested in was the possibility that we might make machines that expressed emotions as well. And for this, we made or rather commissioned from a man in America, a robot head. And you can see him on the right there. So this head has very good prosthetics. The man, David Hanson, who makes these, does prosthetics for Disney and other people. He's very good at prosthetics and can even do a bit of electronics and, motors and electronics and so on inside the head. So this head has 24 motors inside it, replicating the main muscle groups in the human head. And we then dressed up in a shirt and put a wig on it, and it looks reasonably human, and it can indeed express a lot of really quite interesting faces. And you can see the prosthetics are really quite good and dressed up. This is actually modeled on the young Charles Babbage rather than Charles Darwin. Charles Babbage, of course, the if you like, great computer pioneer of Victorian times. Well, unfortunately, although the prosthetics are really good and the still photographs are really quite convincing, the dynamics of this are very hard to get right. And we as people are very good at spotting facial expressions that are somehow not quite right. It's a way of telling that someone's ill. And so most people, we thought we'd do experiments where they conversed with this robot. And what we found was they just found it creepy. Because the movement's just not quite realistic. We did find one application for it, which was training medical students. There's a medical condition called dystonia, where you have uncontrollable spasms of the muscles, particularly in the face. And it's very disconcerting when you meet a patient with dystonia, because their face just is not expressing the normal sort of signals that we expect. Well, this gentleman who has dystonia very kindly agreed to be filmed, and we recorded videos of him and then played them back on our robot. And our robot's really good at uncontrollable facial expressions. And then what we did was take a group of medical students, and some of them had conversations with our robot before they met a real patient and the others didn't. And we actually monitored the students when they met the patient, and the ones who'd been exposed to the robot first had been desensitized and actually could control their response when they saw the real patient. So that was a huge success. It's the only success we've had with this robot, except it wasn't much of a success because it also turned out that if we just showed the students the videos of the man with dystonia, that was just as good as a training tool. So this robot was extremely expensive and really had very little scientific value. But the one thing it's good for is if you have a robot, the press will, especially one that looks like a person, the press will beat a path to your door. And including, this was perhaps one of the more eccentric demonstrations we did. Here you see me and one of my postdocs appearing on a Spanish television show, live television show. It's sort of the equivalent of the Graham Norton show. Even if you take the Now robot, this is a very cheap, popular, cheap robot, which has, well, actually no way of expressing emotions. Remember, the things that matter are the eyes, the mouth. Well, they're just fixed openings. All they can do is light up LEDs in them. And yet people see and these robots are about so tall, and they see them and they immediately empathize with them. And it just says something about the way that people empathize with machines. Although there are two sides to this. The other side of it is when you talk about robots, people ask me about it, they normally begin to ask me, do I think it'll become sentient and turn on me? And that is a constant theme throughout fiction, of course, from golem mythologies through Frankenstein, through to actually a really rather interesting play, Rossum's Universal Robots, written by the Czech author Karel Čapek 100 years ago this year, where Rossum made robots, and this was actually the play that introduced the word robot or popularized it to mean humanoid robots. And the robots, as you can see in the clip there, if you can see, this is a picture from the stage play version in 1921. And the robots are turning on their human creators. In fact, the robots they know there's something different about the humans, and they want to know what it is that's been left out. So they dissect the humans to find out. So it's actually really quite an interesting play, much more interesting than a lot of fiction. And of course, robots have got a fairly bad press in fiction since then, notably in 2001, although actually for those of you who've read the story, you actually know that it's not really the robot turning on them, it's the people controlling it back at base. But of course, those aren't really the robots that we have around us. The robots that we have around us are machines in factories. They're not humanoid. They're just doing repetitive or delicate jobs rather precisely. Or they're running our satellite navigation systems, our mobile phones, our city trading systems. In fact, a robot's anything that takes an input and has an output that produces a perceptible effect in the world. And they're actually the robots that I worry about really much, much more. And it's funny, when people talk about robots, they immediately think about humanoid robots, and they're nervous about them, and they think they're going to take over. Well, they're not really good representations. I mean, our robotic head is one of the best there is, and it's useless. So it's a very poor physical representation. There's no relationship. There's no real emotion. They can monitor and pretend emotions, but they don't really have them. It's not the same as empathy, and of course there's no spiritual dimension. So perhaps the interesting thing is that we don't have relationships with with robots. We may not have a relationship with Europe. And it's this question of sentience is perhaps mistaken. We're imputing machines with personhood, which is just a mistake. And actually the ethical issues, and there are ethical issues, but they're just standard professional ethical issues. What matters is the motivations of the people making them and their competence. So the financial crash in 2008 arguably was caused by incompetent trading systems. And a lot of the problems with Facebook and Twitter is the motivation of the people writing them. They're interested in greed. But this is straying a bit from the technology here. So perhaps that's a good point to stop, and in a minute or two we have left, take some questions. I should perhaps just say, of course, I don't do any of this work myself. I just have lots of extremely bright students who do it all for me. But I will stop there. Thank you very much.
Thank you, Peter. That was an utterly fascinating talk. I really enjoyed it, and I have lots of questions, but we already have 3 questions, so I shall step back. And Bertie, yours was the first question.
Okay, so my question would be, have you come across in your studies any humans changing their expressions to achieve a certain reaction of your detection system, or maybe even avoid such a reaction? And is this something we need to consider for the future? Will misaligned or deliberately misaligned classification algorithms change our expressions in the future?
Yes, indeed. Well, of course, one thing I did say that we did all our early work with acted data that we used for training. And so it was necessarily acted, and even Duchenne knew there was a difference between an acted emotion and a real emotion. And indeed, the tests that we were doing here, we were asking somebody to act as if she was agreeing. Well, she may or may not have, didn't have anything to agree to. She was just doing acting of agreeing. So the answer is yes, they are can absolutely be fooled by acted emotions. Now, there are people who will tell you that they can detect a falsely represented emotion. And in fact, Paul Ekman does work on this, selling the training to people like the Transportation Security Administration in America. There's a suspicion that there are micro expressions in the face, so little flickers of expression that you can't control. And those could be used to detect that someone is dissembling when they're talking to you. Now, that may or may not be true. And most tests of lie detection, however they work, polygraphs and so on, have about a 50-50 chance of working. I mean, essentially they're noise. But what does work is trained security, meaning Secret Service-y sort of people, from interrogation, and they can tell from the way that people tell their story, the way the narrative fits together is actually how you tell that somebody's lying. Our system's nowhere near that. We're looking at very short sections. We're not looking at context. We're not really doing it multimodally. So the answer is yes, these can be fooled by acting. And I think actual lie detection is quite some way off. Of course, doing experiments on lie detection is also extremely difficult. You need to make the stakes high enough, and attaching electrodes to your participants so you can punish them if they fail to convince you is sort of difficult to get through an ethics committee. There are some things you can get through, but that's not one of them. So it's kind of tricky. Yeah.
We have two more questions. I don't know if we have time for both. Depends on what you think in terms of the answer. But the first one from Andrew, he points out that yesterday in our plenary, we had Professor Sophie Scott talking about laughter, and she showed some videos of gestures for expressing emotion that were very culturally specific. She stated that laughter was one of the few positive emotions that is globally recognizable. He notes that sheep obviously express emotions differently, and he asks, does any human culturally specifics reveal themselves in this work? So any sort of culturally specific sort of human...
Yes. Well, I say that interested Darwin. Were these universal? And Ekman reinvestigated it slightly more scientifically, and he was content that at least these basic emotions were universal, and joy, laughter, is perhaps one of those. So that is culturally universal. Was that what your speaker yesterday was saying? But there are other ones that clearly aren't. So, for example, in some Eastern European cultures, nodding your head is a way of showing disagreement, and shaking your head is a way of saying agreement. And incidentally, that's really difficult to do, saying disagreeing and agreeing when you're gesturing like that. So some of these are learned, and that's clearly different. And there are other minor differences culturally, but the basic emotions probably are universal. Yeah, and indeed, some would say that they are also shared by some of the other higher primates. Have facial expressions that are not so different from humans. I mean, I suppose I could show various other species that actually have facial expressions not unlike humans, and Yeah.
Okay, and now the final question from Andres, who asks, well, he points out that a company called HireView uses facial recognition AI to detect soft skills such as cooperativeness and sociability. They ask, how far removed is the facial study of emotions from that sort of use of facial recognition, which has been severely criticized for its lack of scientific basis?
I'm afraid that's what I was about to do, yes. Just as in lie detection, there's really very little hard scientific testing. And Paul Ekman's a good scientist, but he's not published anything in a peer-reviewed journal on the accuracy of these systems. And the work that has been done shows that they're not good. And I have to say, sociability and so on, I find unlikely. And I hope that one of the things I've emphasized throughout is that this is hard. The data are easy to confuse. These are not as clearly cut as we would like to think, clearly distinguished. And that's partly when we've filtered down the information to just that which we can get through a webcam. And particularly if it's just a still picture through a webcam. But then there are the other mental states. So you want to be multimodal, voice and body posture and gesture. You need to know context. Context so important. We sort of saw that with the tennis players. So I'm very nervous about a lot of these automatic system for filtering people for job interviews. There's money to be made from it, I don't doubt, but I'm not entirely sure that they're scientifically validated.
Yes, I think that's a reasonable place to end our discussion. Thank you. That was a wonderful talk. Thank you so much for joining us. And again, for your patience. I know you were supposed to join us last year. Thank you, everybody, for your questions. I could see there was lots of discussion in the chat. I'm sorry we didn't have time to come to everybody. But just a reminder that you can join us for our final day tomorrow. I'll put the schedule in the chat. I hope you'll be able to join us again. And we're ready to close. So thank you again, Peter, and I hope to see you again soon.
Thank you very much. It's been a pleasure.
Thank you. Goodbye, everybody.
Bye.